Hi everybody, and welcome to this session, session 5 of the CSER conference. This session is entitled Threats Without Enemies, Natural Global Disasters and Their Consequences. My name is Lara Mani and I'm a research associate at CSER. And just before we get started today, I'm just going to go through a few housekeeping bits and bobs, and then I'm really looking forward to welcoming you to our panel. So just on the housekeeping then, please note the session is being recorded, but as attendees, you can't be seen or heard, and then the recordings are going to go up on our YouTube channel and onto our website, hopefully next week. If you want to ask questions at any time, please do, and you can either do that through the Hoover questions and answer session on the website or directly into the Zoom chat. And then we have a moderator behind the scenes who's going to feed those questions into our discussion today. We have a hashtag for the conference, which hopefully you will be following anyway, which is CCR 2020. Please do live tweet, and Doug and Lindley have kindly said that they're very happy for you to share the content of their talks today. I'd also just like to remind you about our live artist, Tom McLean, who's joined us today, and I'm sure you've seen him in many other sessions and has been doing a fantastic job of doing live illustrations for us. So watch closely. He's doing some amazing stuff. Okay, with that, let's crack on with the session. So I'll give you a brief introduction. As Martin Rees sets out in chapter 7 of Our Final Century, humanity has lived with global catastrophic risks throughout history. Naturally occurring catastrophic hazards such as asteroid impacts, supervolcanic eruptions, and solar flares are all capable of pushing humanity towards catastrophe. These natural global hazards form something of a baseline against which other risks can be assessed. The scale of these risks may lead us to assume that there's little we can do to protect ourselves, but through advancements in our understanding and surveillance of such risks, we may now be able to reduce our vulnerability and exposures to them and increase our chances of survival. So how do we think about these risks, and what can they teach us about responding to global catastrophic risks in general? To help me answer these questions, I'd love to introduce you to my panel today. Firstly, I'd like to introduce you to Lindley Johnson. Lindley's current role is as Planetary Defense Officer and Lead Program Executive of the Planetary Defense Coordination Office at NASA HQ, where they're tasked with warning and response to any potential impact of Earth by an asteroid or comet. Lindley graduated from the University of Kansas in 1980 with a BA in astronomy and a commission from the Air Force ROTC. He also has an MS degree in engineering management from the University of Southern California. And prior to NASA, Lindley spent 23 years in the Air Force on active duty, obtaining the rank of Lieutenant Colonel with numerous military awards and decorations while working on a variety of national security space systems. My second guest is Doug Erwin. Doug is a senior scientist and curator of paleobiology at the Smithsonian's National Museum of Natural History and external faculty member at the Santa Fe Institute. Doug's research interests involve evolutionary innovation and novelty, particularly during the origin of animals and Permian mass extinction, and the Permian mass extinction and early Triassic recovery, the evolutionary dynamic of the regulatory genome, and the history of Phanerozoic gastropods. Doug received an AB from Colgate University in 1980 and a PhD from the University of California, Santa Barbara in 1985. Doug has published extensively, including authoring and editing several books such as Extinction, How Life on Earth Nearly Ended 250 Million Years Ago, and The Cambrian Explosion, The Construction of Animal Biodiversity. It's my pleasure to welcome both Doug and Lindley to the panel this evening. We're now going to watch Doug and Lindley's pre-recorded talks before coming back for a discussion with the panel and your questions and answers. So please make sure you submit them through the questions and answers box.
My name's Lindley Johnson. I'm from NASA headquarters. I run the Planetary Defense Coordination Office at NASA headquarters, dealing with the risk of an asteroid impact. So I'm pleased to be here to talk with you at this conference on catastrophic risk. My presentation might be a little different than the others in that my job is mainly about eliminating catastrophic risk, or at least reducing it to a much lower level. So all of us know that now this risk of a asteroid impact or a comet impact, cosmic impact, if you will, has been the subject of many movies from Hollywood over the years. Kind of captures the public imagination about what would happen if Earth were to be impacted by a large asteroid or a comet. So it's a staple of the movies, a cinematic catastrophe, but one might think is the catastrophe actually the natural disaster, or is it the movie and the science in the movie? Because they aren't very well, the science isn't very well projected by Hollywood. But here's a few movies over the last few decades that dealt with this subject. There are literally dozens of them. But one I like to point out is one that not as commonly known, the movie Meteor. And it's this is one of my favorite movies because the protagonist in it is a person that kind of plays the role that I am in now was Sean Connery. This is particularly timely right now with his passing over the weekend. And it's kind of a futuristic view in that they showed a position at NASA of a what we would now call planetary defense officer, and this movie was made way back in 1979, almost 4 decades before this actually happened. But the leading theory on the demise of the dinosaurs, the end of the dinosaurs, was a impact of a large asteroid or comet. It's one of the 5 major mass extinctions that is in the fossil record. And the evidence has been piling up over the last few decades that this is indeed probably what occurred. There is a layer of enriched soil, enriched in iridium around the world. And the most likely source of that iridium layer is from a large asteroid impacting the Earth. That was hypothesized and demonstrated by the Alvarez team back in the 1980s, and then this large crater was evidence of it was actually collected in the 60s and 70s, but it wasn't realized until the late 80s and 90s that this really was a crater now called Chicxulub crater off the Yucatan Peninsula in the Gulf of Mexico, crater 150 kilometers across. And that would be caused by an impactor the size of 5 to 10 kilometers in size. And the amount of energy released from that would just be incredible. This is a gravity map showing the existence of that crater. Of course, it's all submerged and covered over by many layers now. But that photo on the right side is me in the basement of the Smithsonian here in Washington, D.C., where they have one of the world's largest meteorite collections. And this, what I'm holding in my hand, it looks like a chocolate layer cake, is actually a sample of that region of the Earth's surface where this iridium layer is, and that lighter layer that I'm pointing at with my finger is that iridium layer. So there's strong evidence that this led to the demise of the dinosaurs. There's also a lot of evidence around the world of craters on Earth. There's more than 190 confirmed impact structures. That means they've actually been surveyed, samples have been taken and proven that these were created by an impact shock. They have all kinds of ages, all kinds of sizes of craters, some examples here. And of course, more recently, in Tunguska, Russia in 1908, not a crater, but over 2,000 square kilometers of forest was devastated by what was thought to be about a 40-meter sized impactor. It didn't actually strike the surface, but detonated several kilometers above the surface, causing a incredible air blast that created this devastation. Impacts, large impacts are very rare events, but can have significant effects. This is a meteor crater here in the US and in Arizona, one of the best preserved craters in the world. The impact occurred some 50,000 years ago by only a 50-meter sized asteroid, but it released energy equivalent to about 5 megatons TNT, and the crater is a little over a mile in size. But the devastation from the blast of this event would have caused catastrophic devastation out to 25, 30 kilometers from the site if it happened in modern day Arizona. So what's the risk here? This is a chart that appears in a lot of literature on this. About different sizes of asteroids and what their effects could be, the amount of energy released, and this average time interval in years between these impacts. So you can see that the smaller the object is, of course, the more frequent, the more there are, and so the more frequently the Earth gets impacted. To get up to areas of regional scale devastation, 100-meter or so sized object, that happens only, every few tens of thousands of years. But I think a chart like this is somewhat misleading and gets misinterpreted because people say, well, the last one happened, 50,000 years ago, and so either we're due for another one or we're not due for another one, depending on your perspective on it. But it's an entirely random event. These don't happen at any regular intervals. The risk is entirely, when it can happen, is entirely random. And it's not like, and it can happen anywhere in the world. So it's not like the risk of getting hit by a hurricane, which only happens half of the year and only in certain parts of the world. This is something that could actually happen at any time, any place. So these kind of charts are a little misleading, I think. But what is valuable for this particular risk is that we can actually determine. We have now the technology and the ability to find these objects while they're still well out in space, long before the impacts, and determine when the next significant impact might occur. And so that's the job of the Planetary Defense Coordination Office at NASA, working with our colleagues around the world in other countries, space agencies, and astronomical institutions around the world. Planetary Defense Coordination Office was established over 4 years ago, and it is our job to manage all the planetary defense efforts across NASA and coordinate also with other U.S. government agencies and the international community to, first of all, determine if there is any significant impact threat lying for us there in the future, be able to assess what the range of effects could be from that impact, i.e. How large is the object, when and where will it impact, and what those effects could be. And then develop strategies with our partners to mitigate those impact effects, be it it's a small object, so all we need to do is evacuate a small area around where the impact will occur, or a larger object, finding it far enough ahead of time that we have several years in which to mount the space mission to deflect it in space. So we're looking for what we call the near-Earth objects. Those are asteroids and comets that come into the inner solar system. This is the technical definition of a near-Earth object, but think of it as something whose orbit can bring it anywhere within about 30 million miles, 50 million kilometers of the Earth's orbit around the sun. And we're particularly looking for what we call the potentially hazardous objects. Those are the ones that come within about 5 million miles or 7.5 million kilometers of Earth's orbit, kind of a torus around Earth's orbit around the sun. And those that are the size that could do significant damage. And the current threshold value we're using is anything that's 140 meters or larger in size, because object that size could devastate a statewide area. If you may have heard recently in the news about NASA's CIRRUS-REx asteroid sample return mission from the orbit, from the asteroid Bennu. This depicts the orbit of Bennu. It is a potentially hazardous asteroid, and in fact has about 1 in 2,700 chance of impacting the Earth in the latter part of the next century, 2175 to 2190 or so. But we can find these objects. Our current search programs are ground-based telescopes that we have mostly in the southwest of the United States or in Hawaii with our astronomical infrastructure there. And we have one space-based asset that we use. It's actually a repurposed astrophysics telescope that operates in the infrared part of the spectrum. Our guidance is from the White House. There was work done through our interagencies for development of a strategy and action plan for a viable response to a near-Earth object impact. Getting ourselves in a better position to, first of all, detect these objects, and then figuring out what we could do about it. And it was released 2 years ago, but it's a culmination of about 4 years of work prior to that. So it started in the previous administration, and that document is available at that web link. We also do a lot of work internationally and with the United Nations Committee on Peaceful Uses of Outer Space. This is a continuing agenda item for that committee. And under the auspices of COPIUS, the member states have set up two entities to deal with this issue. The first is the International Asteroid Warning Network, whereby astronomers and observers and orbit modelers around the world participate for detecting and tracking and assessing any potential impact threat. And then the Space Missions Planning and Advisory Group is a form of the national space agencies to gather and work on technologies and techniques collaboratively for dealing with a possible threat while it's still in space, getting everybody on the what we call the same page. So how are we doing in finding these objects? This is our current discovery rate of these objects, and we're finding close to 2,500 a year now. We actually expect to considerably exceed that amount this year. These are near-Earth asteroids of all sizes discovered by these projects each year. As far as those that are much larger, 1 kilometer and larger in size, we have pretty well cleaned up that population now and found over 97% of those objects were found in the last decade, and now we're working on the smaller 100 meter or so size. We're only finding a few of a kilometer or more in size now, kilometer or two in size each year. So our cumulative discovery with NASA's having started a search program back in '98 we've just gone over 24,000 near-Earth asteroids of all sizes, of which almost 9,400 are 140 meters and larger, and almost 900 are a kilometer or so larger. And about a tenth of those objects are in potentially hazardous objects and potentially hazardous orbits, 2,100 which 156 are 1 kilometer or larger in size. And this goal of finding 140 meter and larger in size is actually directed to us, to NASA by Congress in what we call the George E. Brown Near Earth Object Survey goal. George E. Brown was a senator, the chair, I'm sorry, of the House Science Committee back in the 90s. This population of 140 meter and larger asteroids is estimated to be about 25,000 in total numbers. About 4%, looking at the pie chart, about 4% of that population is a kilometer and larger in size, and we have virtually found all of that, or about 2/3 of the way of having found those 300 meters to 1 kilometer in size. So the real work to be done now is in this area that's smaller than 300 meters, of which we still have over half of those to be found. At our current rate of discovery of about 500 a year, it's going to take us some 30 years to find the rest of this population. So we're working on better capabilities to do that. And since we are a space agency, we can go to space to do this, which would allow us the capability to operate 24/7 continuously, not be affected by day-night cycles and the weather. And we can also hunt for them in the IR part of the spectrum, where they are much more prominent, stand out from the background of stars. And so this near-Earth object surveillance mission, NEO-Surveyor Observatory, would be able to find about 90% of that population within 10 years of operation. We can also, with the IR signature from these objects, make better estimates of their sizes, so we can immediately assess what their effects would be should they impact the Earth. We also operate 2 interplanetary radars. Now, you can't find these objects via radar. You have to find them optically and have a good enough orbit that you know where to point the radars to receive a signal return, and know when to expect that signal return, because you really got to dig it out of the noise to be able to know what it is that you're looking at. Otherwise, it just looks like radio noise. So NASA has its own Goldstone planetary radar in California, and then the large 300-meter dish in Puerto Rico, Arecibo Observatory. And with those capabilities, if the signal return is strong enough, we can actually radar image these objects and determine their more exact size and shape. It's a really odd rogues gallery of these objects. These particular objects here are all less than a kilometer in size, except for Tatatus, is a quite large near-Earth asteroid. We can also determine if they have their own little moons that orbit them, and about 5 to 10% of near-Earth asteroids do have these smaller asteroids that orbit them. Now, most people don't realize that asteroids are coming through the Earth-Moon system all the time. Luckily, most of these objects are quite small. I know you can't probably read this chart, but the numbers, it's more for impact of the numbers. In 2019, over 77 small asteroids came closer to the Earth than the Moon. 77 that we detected, and since we're only looking in the night sky, we know the number was probably larger than that, maybe twice that. but most of them are small enough, a few meters to tens of meters in size, that were they to impact the Earth, they would disintegrate in Earth's atmosphere and just create a large meteor, what we call a bolide. But there are a few that were of significant size, 60 to 120 meters in size. This object, 2019 OK, came within 2/10 of the distance to the moon. In other words, about 40,000 miles of the moon, and distance to the moon. It's a little scary that an object this large approached the Earth, and we didn't actually see it until a day or two before, because of the direction in which it came. And so we'd really like to be able to improve our capability to detect these things further out, so we have more time to do something about them, and that's what the Near Earth Object Surveillance mission is all about. Another close approach that we know about, an example of having discovered an object well into the future, this asteroid Apophis, which will have a close approach with the Earth in April 2029. It's almost 350 meter sized object, so if it were to impact, it would do significant damage. But we know from our observations of its orbit that it's just going to be a close pass on April 13th, which happens to be a Friday the 13th, in 2029. It will pass closer than the geosynchronous satellites, and so it will be an event. This object is large enough that it will be visible to the naked eye, so we can all gather in the Mediterranean area for that evening on the April 13th to see this object pass by. But there are actual other objects, large objects that will become closer to us than the moon over the next decade or so. One example is 2001 WN5. It won't come as close as Apophis. It'll only come about 2/3 of the distance to the moon from the Earth. But this is an object that is as much as a kilometer in size. So that's another significant event that will occur actually in 2028, June of 2028. So let's talk about what we would do about object if it were detected to be on an impact trajectory with the Earth. Impact mitigation techniques. Well, we don't quite have this technology yet from the U.S. Enterprise from Star Trek. But we do have the technology that we think is viable that could be used to deflect these objects in space if we were to find them, able to find them far enough ahead of time, which we have the technology to do that now too. All you need to do is slightly change the orbital speed of the asteroid, just trim a few centimeters per second off its orbital velocity far enough ahead of time, several years ahead of time. And that will cause it to arrive either early or late at the point in space where the Earth is, and be a miss instead of a hit. And three technologies that we've studied for several years. In fact, this is from a report in 2010 from the U.S. National Research Council. Of technologies of a kinetic impactor, which is simply slamming a spacecraft into the asteroid and imparting a force on it, a gravity tractor, and of course the Hollywood solution, which is a nuclear explosive device. But these are all viable technologies that we have in hand that could be applied to this problem. We only have to find them first. The kinetic impactor is probably the most mature technology. As a matter of fact, we demonstrated the capability to do this back in 2005 with our Deep Impact mission, and impacted a comet for scientific purposes to determine what it was made of. And it could be used if we have several years of warning, 5 to 10 years of warning. And then a gravity tractor, which is using nature's own tug rope, gravity, to gradually tug on the object, and that has advantages given enough time of a couple of decades because we can closely control what the new orbit is for the object. Well, let's talk about the Hollywood solution. We wouldn't do as they depicted it in Armageddon or even Deep Impact movies by trying to blow the object to smithereens. That would take a sizable nuclear device and sort of uncontrolled, or have a bunch of buckshot headed at us. Then it wouldn't change the direction. What we want to do is control and change the direction of the object, and we do that by having a standoff nuclear detonation, which irradiates the surface of the asteroid. It causes a blow off of material in one direction, and then the opposite reaction force would be used to change the speed of the asteroid. The gravity tractor, this uses the mass of a spacecraft station keeping beside the asteroid to slowly, with the gravitational interaction between the two over months to years, slowly change the direction of the asteroid. And we could enhance that mass of the spacecraft by going down and plucking a 10-ton boulder off the surface and gathering up in its arms, and then doing the station keeping maneuver. And then finally, the kinetic impactor, which, as I said, was the most mature technology. And in fact, we are now developing a mission to go demonstrate this technique. It's called the Double Asteroid Redirection Test, DART. It is now in its integration and testing at the Applied Physics Lab here in the United States. It is scheduled for launch late summer of 2021. Coming attractions here launching in summer of 2021, and the impact of the moon of the Didymos asteroid system will be in fall of 2022. And we're demonstrating this on a binary asteroid impacting the moon, because this way we're just changing the orbit of the moon about the primary and not changing the orbit of the system about the sun, so we don't impose any additional risk on the Earth being impacted by this asteroid by doing this demonstration. And so that's my pitch, and I'd be happy to then take any questions that folks have about this risk that we have of asteroid impact, and what we now, because we have a space program, can do about it.
Hi, I'm Doug Erwin from the Smithsonian National Museum of Natural History in Washington, D.C. I want to talk today about past biotic crises and how they may be relevant for this meeting. This is an image of a place called Meishan in South China, between Shanghai and Anjing along the Yangtze River. It's a place I've been studying with my colleagues at the Nanjing Institute for more than 20 years now, almost 30 in fact. This is how it looked a long time ago. The red line demarcates something called the end Permian mass extinction, one of the largest biotic crises of the last 600 million years. If we were to walk up through the section along this hillside, we'd see species gradually disappearing from the fossil record. And we'd see the same thing in records at localities all over the world. We've studied Meishan because the record here is more detailed than almost anywhere else. This is a diagram showing the disappearance of species. As we walk up through this section, there are about 330 species here, many grouped into different clades. And this shows a very rapid, indeed a catastrophic extinction close to the boundary. Just an image to show what some of the transitions look like between the latest Permian to the left of the screen with flourishing ecosystems, the earliest Triassic after the extinction with very low diversity, and then later in the early Triassic, an increasing number of species begin to return to ecosystems in various parts of the world. The end Permian mass extinction is one of many events that happened over the last 600 million years. There are 5 canonical great extinctions that are talked about in the press and among paleontologists. This slide shows the diversity of marine organisms over the last 600 million years. And the red arrows show these 5 great mass extinctions. One at the end of the Ordovician, about 440 million years ago, a slow decline during the Devonian, this great end Permian event, and then one at the end of the Triassic, and the famous one that killed the dinosaurs, non-avian dinosaurs, at the end of the Cretaceous 65 million years ago. It's important to note that this record is based upon durably skeletonized, abundant marine taxa, similar to some of these exquisite fossils shown in this slide. We use the marine fossil record because these taxa are abundant, they're geographically widespread, so we're likely to find them preserved as fossils, and they have to be durably skeletonized. They have bones or shells or hard parts so that we can recover them and record their past history. That kind of record produces this outline, this sketch of past biodiversity crises. It's not that plants and insects and vertebrates on land aren't important. We simply don't have the resolution in the fossil record that allows us to look in detail at the timing and the nature of the events, although the record for all those other kinds of fossil groups is much better than it was a few years ago. A more detailed look at this kind of data shows that these biodiversity crises go far beyond the 5 that are popularly known that I showed on the previous slide. This shows 18 events over the same period of time, the last 600 million years, that are outlined in red, each of which has heightened extinction relative to the surrounding intervals of time. This is a slide from a paper that I published with my colleagues in South China in Science in January this year, showing us a very high resolution record from China, essentially the entire Chinese fossil record for the period between about 540 million years ago and the great end Permian mass extinction that I've been talking about on the right, catastrophic drop. And you can see that there are many ups and downs and squiggles superimposed on this line, showing that biodiversity crises happen at different scales. Some of them are these catastrophic events, some of them are much smaller. During these events, we know that they're selective in different ways. Some taxa are more likely to go extinct than others. The reasons for these selectivity are not always clear. Often they seem to have to do with metabolism, with geographic range, or other factors. But they do provide clues that are important for understanding the nature of these mass extinctions. And we can identify a number of common features of these events. They're geographically widespread. They're found essentially globally, often both on land as well as on the sea. They're selective in that particular groups are affected more than others. And there's a common underlying cause, in most cases, of rapid climate change. This is a slide or an illustration from Siberia. It shows a massive flood basalt known as the Siberian flood basalt that covers an area almost the size of the continental United States. It erupted rapidly, and we're fairly convinced now that this is the major cause of the end Permian mass extinction, this event 251 million years ago. These massive flood basalts are one of the leading causes of these past mass extinctions. In general, the mass extinctions are associated with climate changes, particularly global warming, and often oceanic anoxia, loss of oxygen, particularly in shallow waters. But the ultimate causes are these incredibly massive volcanic eruptions. And in one case, at the end of the Cretaceous, impact of an extraterrestrial object. One of the important features of these events, though, is that the context matters. Not all massive volcanic eruptions have caused severe mass extinctions, and not all impacts, because they vary in size and where they hit, have caused mass extinctions either. So where these events and the nature of the Earth system at the time they occur plays a very important role in the size of the events. This is an illustration showing the distribution of these flood basalt provinces. You can see that many of them are quite massive in size. The Siberian flood basalt one is huge. Some of the other ones are much smaller and had much less, possibly no real biotic consequences at all. So in summary, mass extinctions and biodiversity crises have been ubiquitous in the history of life, at least the history of life we know over the last 600 million years. The primary cause of these events has been rapid climate change, most commonly triggered by massive volcanic eruptions. We have relatively suggestive evidence that resilience to extinction during background times, the intervals between these mass extinctions, often enhances survival during great mass extinctions. And that may be of some relevance for this conference because it suggests that fostering resilience during so-called background intervals may also guard against or enhance survival during global catastrophes. Thank you.
Thank you both for those brilliant talks. And I've watched them many times and I still love them each time. So, you know, we've chatted many times and you know that I will ask you questions all evening. So we've already had loads of questions coming in from the audience for your talk. So I'm just gonna hop straight over to a few of those and then we'll kind of head into the discussion where we're kind of going from there. So Lindley, there's a lot of similar questions coming in for you. Around the uses of the technologies that you describe for asteroid deflection and kind of talking around whether is there technological political risks of launching nuclear weapons into space, for example? Does that outweigh the potential benefits of asteroid deflection? Could these technologies be actually used for bad?
Well, first let me say that that's not an option we want to try to use. It's kind of a last resort option if the object is particularly large and particularly close to impact, i.e. we haven't found it before we get into a situation where that's that amount of energy is our only response that we could undertake. But the other thing is that's also exactly why that we work this potential issue for humanity with the United Nations Committee on Peaceful Uses of Outer Space and have set up these two entities that I talked about, the International Asteroid Warning Network, so that the entire world, astronomers around the world are involved in that and can work with their communities, nations, and governments in understanding what the potential threat is. And then the Space Missions Planning and Advisory Group, which is a forum for agencies around the world. We are some 16 now, different space agencies around the world. US, ESA, Cosmos, Roscosmos, the Russians, even the Chinese Space Agency is participating in this group to get everybody on the same page as to what is the response that the world should take for a particular threat. And these kind of issues that you are being questioned now, actually we've had a ad hoc legal working group made up of experts of space law, international treaties, look at these issues and have produced a report that you can find from the same page website.
Okay, and kind of just following on with that, Lindley, you mentioned a little bit in there around that it's kind of seen on NASA's shoulders currently to alert the international community about a potential object that might be coming our way. Are you the only ones that are currently monitoring and following these? And this question comes from one of our research associates, Clarissa.
No, we participate, or major participant, of course, but we participate with this International Asteroid Warning Network, which has astronomers, orbit modelers around the world that are looking at this issue. The European Space Agency has a similar office to ours at NASA. We have participation again from Russia, Korea, the Chinese are all involved, and all the observations and data goes into the International Astronomical Union's Minor Planet Center, where everybody has access to that data.
And there's one point that you both allude to in your talks, Doug and Lindley, together. So I'd really love to kind of hear from both of you on this. And it's around, sorry to say, I mean, Lindley, you named your talk around what if dinosaurs had a space program, so I can't not mention dinosaurs, right? And basically, I want to know really, is the event that wiped out the dinosaurs an act of misfortune? Is it, Doug, you talk around these scenarios about where this might actually, how the scenario in which it might impact actually could catapult these kind of events into catastrophe. And I wonder if you can elaborate a little bit on that.
Which one do you want to have go first?
I think it
Well, I mean, so one of the points about the end Cretaceous mass extinction is that the bolide happened to hit the Yucatan, and it came in at a relatively low angle, I guess, from the south, roughly. So because that was a large carbonate platform, and because of the direction of the bolide, that appears to have had different consequences than if, for example, it had hit in the middle of the ocean. So, if the orbit of the Earth had been off slightly, if rotation had been off slightly, the consequences of that event might have been much different. So that's why I think context in these things does matter. It's not that you'll get the same effect every time you get an object of the same size hitting the Earth.
And Lindley, you've briefly mentioned something to me in our preparation chats around that you're doing some modelling with NOAA around the scenarios of what might happen if it impacted on a water surface.
Right. Yeah. As I mentioned, that one of the things we're tasked with is assessing what the effects could be of any particular impact event, so that we can inform leadership, decision makers on what is the proper response given a certain situation. That they all are going to be a little bit different. One of our challenges is collecting enough data on a particular object to be able to make a assessment that has any credibility to it. And so we've been doing a lot of modeling of different scenarios, different size objects, different compositions, different trajectories for how they strike the Earth, where they strike the Earth, and those kinds of things. And so part of that is modeling the Earth environment, the oceans, and such. And we do that with the participation of NOAA. We've done some significant work with them about tsunamis that could be caused by a impact. That's one of the big effects in the Hollywood movies is, it plunks down in the middle of the ocean and we have this big tsunami that comes in and wipes out New York City. And found that it isn't as significant as once thought. It's not quite the same mechanism that's caused by an earthquake, a subsurface sea earthquake. The energy coupling is significantly different, and so you'd have to have a really sizable asteroid, kilometers in size, or a smaller asteroid that impacted nearer the coastline to really have any tsunami. And so that's the work we do with NOAA.
And I have one just question that's come in from one of our visiting researchers, John Fogel, and he's asking specifically about for you, Lindley. What if this happened today? Are we in a position where we can launch a DART system, or what would be our response if we, for example, one of these unseen objects coming from the day sky? What would our response be?
If it happened today, we're not quite there yet. We have a ways to go. That's what our preparedness plan is all about. It's actually a 10-year plan to get us in a better position to handling these kinds of things, and working with our agencies and international partners to improve our capability. So we're not there yet, but our understanding and technology is within our grasp, with a little bit more application of resources against it to eliminate this from our list of catastrophic risks.
And I think that's a really important point on that, Lindley, that this is one of the reasons that we actually focus, or you in your line of work, and the US government as well is focusing a lot of kind of attention on this, is the fact that it is a risk that we can mitigate.
Yeah, it's one of the few natural disasters that we have some concept of how we might prevent it. Let's work on it a little bit more so we are in that position here in the not too far distant future.
Okay, and turning to you, Doug, I think you raised some really important points for this discussion, and something that perhaps wasn't touched on quite so much in Martin's original chapters. And I guess one of the things that really strikes me about your talk is this kind of connection between volcanic activity and climate change, and that as a driver of actually more of these extinction events. Typically we think of mass extinction events and we think about Lindley's work and we think about these asteroids heading straight for us, but actually the narrative is very different, and I think that really shines through in your talk. And I wonder if you can kind of elaborate a little bit more on that, about when these become catastrophic and what these extinctions could actually be like.
Those are great questions. Unfortunately, they're also the ones that are hardest to answer. When I say that the Permian mass extinction was caused by this Siberian flood basalt, what I'm really saying is that there's a close temporal correlation between the two. The harder part is actually making the causal connection from the eruption, release probably of a lot of sulfates and CO2 and other gases, and actually killing brachiopods or dicynodonts or something that was wandering around in the Permian. Because we're going back 251 million years in time, that's much harder to do. But the belief at this point by most of the geologists working on this sort of thing is that the cause of the extinction is largely a combination of the immediate release of sulfates and other gases by the volcanism, as well as climate change. And initially probably cooling, but then we think there was probably a rapid 5 to 6 degree increase in temperatures associated with this at all as well. So it's a combination of things, and it eventually becomes a network effect. If I ask you what caused the great outage in the eastern side of the US when the electrical grid went down a couple of decades ago, you could say, well, I mean, we know that that we can trace it back to a particular place in Ohio, I believe, where the initial disruption happened in the network. But the real cause of that electrical outage was how that percolated through the network. And in an extinction, we have to look at how it percolates through an ecological network. And those are still questions that are under very active research at this point.
So that's really interesting, because you're talking about it in terms of it being a combination of both climate change and the release of gases from a volcanic system, which essentially, without the volcanic system that we're seeing now, we're seeing a much more anthropogenically driven change to our climates. So do we think from your kind of work and what you kind of know from the fossil record that we could infer something around a biotic crisis in our current direction?
That we could infer one?
Yeah.
Well, we're certainly doing, making a lot of changes to global climate. And for a variety of reasons, humans have already induced a lot of extinction, and there's a lot of extinction debt that will play out over the coming decades and centuries. Whether or not that will lead to an extinction of the same magnitude as what we've seen in the past in the fossil record, I think, and this is controversial, is a little unclear, because most of the things that have been extinct in the past are these geographically widespread, durably skeletonized marine taxa. And most of those have not yet suffered the kind of extinction that we've seen among plants and insects and terrestrial vertebrates and things like that. one of the examples I often use is the passenger pigeon. There used to be 5 billion passenger pigeons in the 19th century in the United States, but as far as I can tell, there are 2 fossil records of passenger pigeons. So you had a standing crop of 5 billion birds for centuries, but only 2 of those are known from fossil records, non-archaeological context. So even something as abundant as a passenger pigeon doesn't actually wind up in the fossil record. So you lose a lot of taxa without getting to the magnitude of the extinction that we've seen in the past. That doesn't mean what we're doing now is a good thing or that the Earth will recover from it quickly. But the magnitude of extinctions that we've seen, that we've documented as paleontologists, are far, far worse than I think most non-paleontologists recognize.
And I think that that's, again, something really interesting as you talk about the recovery of species. And I think it's really important that we talk about timescales here too, Doug. We're both geologists. We don't think in timescales quite the same way as many other people. So when we're talking around recovery of the species and, this kind of evolution of the marine taxa that you've seen in the fossil record, what kind of timescales are we looking at?
Hundreds of thousands to millions of years. You do see some initial recovery on the timescale of tens of thousands of years after the Cretaceous, and to some extent after some of the other events. But after, for example, the Permian, there certainly was a response on the timescale of hundreds of thousands of years. But the recovery really took at least about 5 million years. So considerably longer than humans have been on the planet before you saw a real biotic recovery from that event. So these are not things that the Earth recovers from quickly, even on a geological timescale.
Absolutely. So we're talking about your work here, Lindley, and unfortunately we're not in a position right now to potentially protect ourselves if something was heading our way. What kind of timescales, and I think you alluded a little bit to it in your talk, are we talking about to have this technology live in order to be able to be this mitigation of an object heading towards us?
Well, it all comes down to money. We have to have the necessary resources put against it that, we can build the systems, like I mentioned, the Near Earth Object Surveillance Mission, to find these things where they are still well out in space. So we have the time that we would need to intercept them in space. But we're not talking $1 billion a year program by any means either, at least not until we actually find a threat. The monitoring and finding these things is, currently, just so you know, our budget in the US for this right now is $150 million. It could stand, to really get us in a better position to be, 50% more than that or such. We are able to do this DART demonstration on that budget right now. A little bit more of a push would get us, and a decade of that kind of funding would get us over that hill.
This is something that seems to really ring to me from when Nancy Connell joined us yesterday and was talking around pandemic risk. And she said, this is a risk that we can mitigate and we should therefore been prepared. We should have had all these processes in place. And it seems like NASA's on the road, or maybe even the global community is on the road to doing that for asteroid risk. But we're talking about all natural global catastrophes. So what does that landscape look like for things like solar flares or, supervolcanic eruptions? I'm smiling because I get to mention volcanoes.
These kind of things take thinking on the order of, decades in the future, not to the next election cycle. So.
Very key point. Again, we've heard that many times. I think echoed throughout the conference with nuclear disarmament and other risks. So this problem of short-term thinking in governance. From my kind of view, and Doug, and please do come in. I think that we have quite a good surveillance network of some of these hazards in place.
we certainly do for volcanic. I mean, there's a robust global seismic network that was originally established to track nuclear testing back in the 60s, but still exists to track earthquakes. So if something like a super volcano, another flood basalt was beginning to develop, geophysicists would know about that, long before it happened, I think. The problem is that other than fly there to watch, which I suspect a lot of volcanologists would do, yourself included, I'm not sure what we would actually do. I mean, as I mentioned to you earlier, one of my favorite quotes from Will Durant is that civilization exists subject to geological consent. And there are some risks which the proper response is, as was discussed for pandemics, is developing a robust ability to withstand these sort of shocks rather than actually mitigate the shock itself. That's this, we're not going to mitigate earthquakes in Japan or in California. What we do is try and prevent as much damage as we can by changing building codes and building robust networks to withstand that sort of shock.
Yeah, I kind of echo the sentiment. For me, a lot of my work focuses around on thinking about these global catastrophic risks, but actually, and maybe it's fair to say that the hazard element of these risks has remained fairly constant throughout geological history. I'm hoping that's true, Lindley, on the asteroid front. But actually, the vulnerability element of that risk has altered because as humans have developed, we've become much more exposed to the hazards through the way in which our global systems produce. So that's again something I think is really missing from Martin's book, is this kind of talking about this link between the hazards and the vulnerability to escalate that risk. So yeah, I really appreciate you bringing that through, Doug. And I think as well, one of the other things there as well, and we're talking about our kind of global system right now, it's pushed and it's stressed to different directions around the climate crises, and it's pushing natural hazards into the realm of disaster causation that perhaps we hadn't have thought about before. And so, Lindley, one of the questions I would love to ask you is, what is that critical? I mean, you talk about the 1 kilometer being the catastrophic size. Could that necessarily be true? Could there be something smaller that led us to catastrophe?
Well, it all depends on your definition of what a catastrophe is, and that probably varies depending on how close you are to, to where the impact is. For a global catastrophe, yes, it would require an object, at least we think, according to our modeling, an object at least 1 kilometer in size to cause effects around the world. But, a 100-meter size object hitting somewhere along the eastern seaboard in the United States would be considered a catastrophe. Yeah, certainly for the U.S. So, or any, anywhere else in the world where there are major metropolitan areas, because the 100-meter object, would cause a crater anywhere from 3 to 5 kilometers in size, and then the area of air blast, a radius of air blast from that would probably extend out to 50 kilometers or so at pressures, that would certainly knock down wood frame buildings, if not more sizable structures.
I've had another question in that is to both of you, and it comes from Matthias Mass, who's one of our research associates at CSER. And he's saying, linking to the themes of the session, threats without enemies, do you feel that the national and or global response to these types of disasters is improved by the fact that there is no enemy, that it's more of a global threat? Or is it more that there's more public attention towards them? What is it that's bringing them to the top?
Well, go ahead, Doug.
I was going to say, not entirely facetiously, the fact that the impact killed the dinosaurs and everybody loves dinosaurs, at least when they're 5, doesn't hurt. I mean, dinosaurs are these big fierce things that we don't actually have to worry about. And the impact at the end of the Cretaceous certainly has captured attention more than supervolcanoes. There's a charismatic element to this too, I think. But go ahead, Lou.
Well, what I was going to say is, it's kind of in the title, Threats Without Enemies. It means that it's, a threat against the entire human species. And so, that there's nothing that brings you together than a common foe. And I think it's something that, the international forums that we have, like the Committee on Peaceful Uses of Outer Space, it provides a topic that the nations can coalesce around and work together to try to solve. And that leads to benefits in other areas in dealing with other problems as well. So that is sort of why the asteroid impact threat has been a area of interest in developing better international cooperation within the Committee on Peaceful Uses of Outer Space.
Doug, I want to come to you on one final question, and that's around the resilience you talk about. And I would really love you to kind of elaborate a little bit on that. We've only got a couple more minutes left, so I'd love you just to elaborate a little bit on what resilience could look like just before we come to a wrap up.
Well, resilience, in a sense, is another one of these network issues. It's how do you keep the network that underpins civilization, whether it's economic, social, political, working in the face of some of these threats. And the point that I made at the end of my talk, that resilience, that we have some evidence, although it's a controversial issue, that resilience during background times can enhance your resilience during the catastrophes, suggests that perhaps if we're concerned about existential or catastrophic risk, we should also be paying attention to the resilience of our other systems during hurricanes and earthquakes and the sorts of things that happen on a much more rapid recurrence cycle. And that does require skills in a whole variety of areas, including understanding network dynamics. So some of the math for understanding the networks that underpin the electrical grid actually didn't exist 5 years ago. The math is actually itself a hard topic. And those problems have also only been solved relatively recently. And I think by integrating across many of these different disciplines, we may be able to see how to develop more resilient systems.
I think that's a really, really perfect point to kind of come to a kind of wrap up. And I guess just as my final question to both of you, as I would really love to know what we can take from both of your respective fields and kind of use for other global catastrophic risks, and what we can kind of learn for those more developing fields. Lindley, do you want to go first?
I don't know if I quite caught your question. Maybe Doug has something more immediate to say.
Well, I would just emphasize the fact that, as we heard with the pandemics yesterday, there was nothing about what happened this year that was a surprise to anybody who'd ever read anything about epidemiology. And if taking the longest time scale that we have as geologists, we know that these sorts of biotic crises happen fairly frequently in the history of life. And we will face, whether it's an impact or supervolcanoes or probably much smaller events in the future. The question is how we're able to respond to those. And we didn't do terribly well this year.
Yeah, I think it's all in a question of of how we prioritize these hazards and threats. Although I would be the first to say that dealing with asteroid impact is not the highest priority thing on NASA's agenda. It is something that should be somewhere in that list of priorities and be steadily worked upon. You know, the thing is that time is on our side of you know, the interval between impacts probably means we have years to decades to work on this and get ourselves in a better position. And so, but we shouldn't waste that time. We should be working on these issues on a continual basis, because if you wait until the threat is realized, it's too late, just like with the pandemic.
Well, and of course, that's what's happening with climate change. Essentially, we've already baked in the fact that there's going to be a substantial increase in global temperatures by not responding effectively to that.
Okay, well, unfortunately, that's already the end of our session. So I'd just like to thank both Lindley and Doug for joining us today for such a brilliant session. And as Doug mentioned during his session, he shared a few weeks ago a quote with me by the historian Will Durant, which is that civilizations only exist subject to geological consent. And we've chatted recently since, and we've decided that it needs an appendage, which should be unless we can change the rules. So I guess that kind of sums up our session. So next up, thank you for everyone. First of all, thank you for everyone that's engaged with us, and please do continue to answer questions, and I can very happily forward them on to Lindley and Doug if there's many I can see that I haven't answered. So thank you very much for those. So next up is the Global Catastrophic Quiz, and I'm going to hop over there quickly because I'm one of the quiz masters. And so please do join us. And if you've signed up for a team, you've got your team groups to go and join into, and there's answer sheets to download. Yeah, that's up next. And then we'll be back again tomorrow with 2 more panel sessions too. So thanks, everybody.
Thanks for bringing us together.
Thanks.